So today we're going to talk about 2D problems. Particularly with scalar field variables. So we're kind of taking baby steps. We did 1D, now we're going to do 2D scalar field variables. So when I'm talking about scalar field variables, like pressure, temperature, right? The next step will be to talk about elasticity problems where it's also 2D, but now every node has 2 degrees of freedom. Right? Displacement X, displacement Y. So that'll be the next thing, right? But so first, just some general comments about 2D problems. Of course, in 1D, we didn't really have to worry about discretization error, right? I mean, if I'm discretizing, if I have a line and I'm discretizing it with a line, I can always have a perfect discretization, right? So there's no discretization error, no mesh error in 2D, but in 1D rather. But of course, in 2D, I have an arbitrarily shaped domain, and I have to cover it with elements, and there's some choice in which elements I want to use. For example, I could use triangles, but if I'm trying to cover any arbitrarily shaped region with essentially polygons, I'm always going to have some error due to the inexactness in the geometry, right? And of course, I could also choose to cover it with quadrilaterals. Okay. So I have a lot of choices here. I can choose, as an analyst, I can choose the element type. So that's in 2D, usually just triangles or quads. Although more recently, as an area of research has been to also work on polygonal elements. But of course, to construct the shape functions for polygonal elements is a little bit difficult. Much more difficult than triangles and quadrilaterals. So we also can choose the number of elements, which of course also implies the size of those elements, right? So we could have lots of small elements to reduce the geometric error, right? The mesh error. But we could, that's going to increase the computational expense. We could also have, we can also choose the degree of accuracy. So that is the interpolant order, right? So, you know, technically, if I have a quadrilateral, even though it has, this thing has 4 sides, if I discretize it with biquadratic shape functions, each of those sides can be curved, because if I have 3 nodes, along an edge, then I can interpolate it with a quadratic, so I can have a curved edge. So we can also use the polynomial order of the interpolant to reduce discretization error. Right? And in the end, though, there's no magic formula. I mean, these are things that we have to consider as an analyst. And quite frankly, because there's no magic formula, I mean, this is really the reason that I think it's important to go through and see all the details of the finite element analysis, understand how to program it, understand the underlying assumptions. Because if you don't do that and you just go run abacus and you have no understanding of what's going on here, you don't know where your sources of error are, and you really don't have any knowledge to tell me if your solution is correct or not. Because I mean, the computer will certainly give you an answer. But if I follow it up and say, well, is that answer correct? You know, without any sort of knowledge of the assumptions that go into the choice of these things, it's very difficult to tell me if it's correct or to prove to me that it's correct. Right? So there's no magic formula, and these things, you know, come with experience as an analyst. But we do have some sort of rules of thumb. So it's called general rules. So, I mean, one is sort of obvious. The element should be able to reproduce fields on the order of the governing equation. In other words, you know, it's real popular now to do phase field modeling. And there's a so-called fourth order phase field theory. So you have to solve it like a fourth order PDE to solve for this scalar field. Well, you can't solve for a fourth order PDE if you have a linear interpolant element, right? Because when you go to evaluate the partial derivatives, even after your integration by parts step in a fourth order PDE, you're still going to be left with two derivatives on your shape function. So if you have linear shape functions and you need to take two derivatives, the field's going to go to zero. So that's sort of kind of obvious. So you want to choose a number, a shape, a type of element that leads to an accurate solution. And you know what I mean there is, don't do something silly like take this domain over here and you know, mesh it with two triangles. You're not going to get a very accurate solution that way. So 3, the mesh density should cover areas with high gradients. Right, so if we have a part like this, and we fix the bottom, and we apply a force right there, we know that there's going to be stress concentration at that corner, right? So when we design a mesh for this guy, we want to refine it in regions where we know there's going to be high stress concentrations. Right? And we want to grade away from those gradually. So I'm going to say grade away gradually. So in other words, you don't want to, you know, you wouldn't want to have a really, really fine mesh here and then just immediately go from one element that, you know, one element that has an extremely fine mesh to immediately to a coarse one. Right? You'd want to grade away more gradually than that. And a lot of times your meshing softwares can help you with this problem. And of course now we also have very good adaptive mesh refinement that we can implement in the codes and help us adaptively refine according to some error estimation. So it sort of can figure out where areas of high gradients are, where this error in the solution is likely to be high, and it could automatically refine that region. So in a say wellbore well, I guess I gave away the answer. But I was going to say in a reservoir geomechanics simulation, where would an area of high gradient be? High pressure gradient near the wellbore. But of course, you'd also, if you're actually doing the finite element analysis, because of the geometric accuracy issue, you'd probably likely have a fine mesh near the wellbore anyway, because you need the fine mesh to resolve the wellbore.